video, I'm going to be talking about how to draw force diagrams or free body diagrams. Books sometimes use them interchangeably. I use them interchangeably, so a force diagram or a free body diagram. You're going to do these for pretty much every single problem in physics. So better get used to doing them. And that's why we have an entire video just about how to draw them. So force diagram or free body diagram. So forces. What was it that I said you have to remember when we're talking about forces? Go back to your notes, look it up. What would it say? When you hear the word force, what did I want you to remember? Forces are interactions between two objects. So forces are interactions between two objects. Can't be three, can't be one, can't be zero. It's interaction between two objects. And what a force diagram is, or a free body diagram is, it's a picture, a diagram of all the forces that act on an object. So when you're holding something, so I'm just going to hold something, and I'm just holding it there, I should be able to list all the forces that are acting on the object of interest and be able to tell you what other object is causing those forces. So when you're going to do this, step one is choose what object you want to do the force diagram of. So in that case, I'll do the little brush. Second, draw the object not as a beautiful rendition of what it is, but draw the object as a box or a circle or a dot or something like that. And then three, draw vectors, because forces are vectors, they have size and direction. Draw vectors that start on the object. And I'll show you a good example and a bad example. Draw vectors that start on the object, and then label each of those vectors. So label each of those vectors so that we know what they are. So those are just the basics of how to draw a force diagram. And let's go on to an example. Poof, just like that. The board is clean. Isn't technology marvelous? Okay, so for an example of me holding a brush in my hand, let's do the force diagram for that pretty simple thing. If I draw the actual picture, you know, there's, oh, I don't even know what that thing looks like. There, something sitting on my hand. So what object? Choose the object. Well, I'm going to do the forces acting on the brush. So my object is the brush. And then draw it as a box or a dot or a circle. I tend to go with boxes for some reason. I don't know why. It doesn't matter. Just don't draw the actual object. The point is that this is just a representation of something. Okay, so there's my box, which represents the brush. And now we're going to talk about what forces act and draw those forces on the box. Okay, so when I'm holding something in my hand, what forces act on that? Well, we know that it's being pulled downward by the earth, and that is the force of gravity, which is weight. So there's a downward force, and some books, I'll just show this to you once, some books label it as the force of gravity. I'm just going to say it's weight, because those two are the same thing for our purposes. So earth, and that's the object, earth is pulling downward on the brush. All right. And now, if this were the only force acting on it, well, you know what would happen. It would fall at a rate of 9.8 meters per second squared. And so there must be something keeping it from falling. When you're holding something up, it's you. You are doing that. And now, what type of force is that? You probably want to say it's a push or a pull, but that's not right. That's not really what we're talking about when we're talking about pushes or pulls. In this case, when something's just resting on a surface, that surface is exerting an upwards support force, a reaction force. And that force is the normal force. Usually we just label that with an N. So here we have those two, and now when something's resting on my hand, are any other forces acting on it? Well, is anything else interacting? Is anything else around the object interacting with it? No, we're done. And now you'll note, I start my vectors on the object. I don't want to see this kind of force diagram. That is not what we want to see. We want to see the forces starting on the object. Otherwise, you might get really confused later on when we're dealing with angled objects. So this is a basic, simple force diagram, two forces, and I've drawn them equally. You can probably figure out why I said they have to be equal, because if something in my hand isn't moving, you probably have a good sense already that those forces better be equal. And now every time you have a force, you have to be able to say, what is the physical object causing that force? In the normal force, it's my hand exerting an upward force. With weight, it's the earth pulling downwards on it. We can name them, they're real forces, we're good. So let's do a little more interesting example. How about, how about something, an object on an incline that isn't moving, okay? So an object, we're going to use eraser as the object, on an incline, and it's holding still. So that's the situation. What would that force diagram look like? Okay, well, the picture is just, there's my basic picture, sorry, cat. And let's start with what forces are acting on it. Okay, there's my eraser, just a box. So what forces act on the eraser? Well, if we're on the surface of the earth, you're pretty much guaranteed there's always going to be that weight force. Always a good one to start with. What else is exerting a force on the eraser? So it's sitting there, and again, something's holding it up. What's holding it up? The box was. So the box is exerting a support force, a reaction force, which is the normal. But what you have to remember about the normal force is it's always perpendicular to the surface. The normal force is always perpendicular to the surface. That's why we call it normal. It's a mathematical term for perpendicular to the surface. So in this case, the surface is like this. Perpendicular to the surface is like that. So the normal force is going to be along this line. Now, which way is it going? Is it going downward like that or upward like that? Think about it. If you think about it as a support force helping keep it up, then we have a normal force looking like that. All right, is there anything else that is acting on the eraser? Earth, the box. Well, I would think that we'd be done. But if you look at this diagram, I look at that and I say, okay, so there's kind of up, down, there's even up, downs, but then I have a sideways force. I have something that is exerting a sideways force on it. And that means that it should be moving in that direction. So I must be missing something. What am I missing? What other objects are interacting with the eraser? Well, in this case, the object is again the box. And let's think about it this way. So I start like this, and then I slowly angle it up, and at some point it starts sliding. Why does it start sliding? What's keeping it from sliding? How about that? What's keeping it from sliding? There's your answer. You probably can guess that it is friction. So friction, the interesting thing about friction is that it's when two things are trying to rub across each other, rub together, and friction always has to be parallel to the surface. So if this is the surface, friction is in this direction. So it either goes up like that or down like that. Which way do you think it's going to go? Make a prediction. Do you think friction is pointing that way, or is friction pointing that way? One way to think about it is that, again, friction is kind of holding it up, keeping it from sliding down, so it's resisting a downwards motion. So friction is pointing up in this direction. All right, anything else? This kind of evens out because these two left, right even out, and then we've got up and down, which will even out. So yeah, this could hold still. Is there anything else physically, any other physical object interacting with it? Well, you might say, what about my hand? I'm holding up the box, right? So why isn't the force of my hand here? And that's where we have to be careful, because this is a force diagram of the eraser. I chose the eraser as my object. That was my object, so I'm only doing the forces on the eraser, not on the box, because I'd have to do a separate force diagram for forces on the box, but just on the eraser. And in this case, we're done. So what physical objects cause these three forces? Well, weight. Weight is the earth pulling down on us. The normal force is the surface, the box pushing up to support it. And friction is the box trying to resist that sliding motion between the eraser and the box. So this looks good. All right, one more example, and I'm going to give you a tricky one. So, if I don't know if I can do this, through the blanket, no I can't. Okay, we'll just do it here. I can push on a marker just with my hand, just with one finger, maybe, and I can hold that marker steady against the glass. Take a minute and see if you can figure out what forces must be acting on the marker. So our object of interest is the marker. What forces act on the marker and what directions are they? Give it a try while I am erasing some stuff. And it is a sneaky one. Oh, shoot, I didn't want to erase that. I'll redraw that. Okay, so normal force is perpendicular, friction force is parallel. Okay, my basic picture, here's the wall, here's the marker, and there's my finger holding it against the glass. Okay, so that's my picture. The object of interest is the marker. So there's the box that represents the marker. What forces act on it? Well, as I said last time, if it's near Earth, we can pretty much count on gravity. So we've got our weight, which is the Earth pulling down on us. What else is acting on this? Okay, well, clearly my finger is pushing on it. So I am going to say there's a push of my hand on the marker that direction. Again, start your vectors on the object. Start like this. So this is the force, you could call it the force of the push, you could call it the force of my finger pushing on it, however you wanted to label it, so long as it's clear that that's what it is. It doesn't matter that my finger is physically on this side of the marker. I don't care about that. All I care about for a force diagram is what direction the force is in. So be careful when you're drawing that. Always start your vectors on the object. Okay, what else is acting? And now you probably say there's a normal force because something's being pushed against another surface. And you could probably guess that there's friction involved too. But here's where we have to be careful with directions. Yes, there is a normal force. Yes, there is friction. What directions are they? The normal force is always a reaction to a push that is perpendicular to the surface. Here my surface is up, down, which means my normal force must be horizontal. And which way is that going to be? Well, the normal force is the wall pushing on the marker. In that case, I'm going to say the normal force is in this direction. And then the same thing for friction. If I push it, I can hold it still, or I can let it, if I let it go a little, it starts sliding down. And so we do have that other force of friction, but again, friction is resisting sliding motion. The marker wants to slide this way, and so friction, opposing the motion, wants to slide downwards that way. Friction's going to act upwards, holding it up. So even though your finger, you think about it, it's like my finger is holding it up. No, my finger's pushing on it. If my finger were holding it up, that would be holding it up. My finger's pushing on it, but what really is holding it up is friction. And so we've got this one here. Now let's make sure we know the physical objects that belong with all these forces. Weight, earth. The normal force, it's the wall. Friction force, it's also the wall. And the push, that's caused by my finger, so you could label it either one of these. All of them have a physical object acting on the marker, and with those 4 forces, I can see them easily balancing out so that the marker just doesn't move, it's holding still. So there is the basics. There are the basics of drawing free body diagrams or force diagrams. And just, you'll want to get a lot of practice on this because every single force problem you solve, you'll need to do this. So get lots of practice, and it hopefully doesn't seem too hard. Just a question of, okay, thinking about the directions and keeping those in mind. Good job.